Hello, lovely humans, Jen Foxbot here. I'm really excited for today's Math Mondays topic. Still in electrodynamics, there's a lot of stuff to cover, but we have made it to Faraday's Law. Yes! Okay, so for real, this is one of my most favorite discoveries in science. I don't want to spoil all of it. There's a little special secret at the end, but essentially, without totally ruining it, Faraday discovered that the electric and magnetic forces are the same. So cool! And again, that's not spoiling this super special surprise at the end. It has far-reaching implications, even beyond electricity and magnetism. So, how did Faraday discover this? What was going on here? Okay, so Faraday did 3 different experiments. The first experiment, he had a magnet and a loop of wire with a resistor or something, and he pulled the loop of wire through the magnetic field to the right and discovered that a current flowed through the loop. Okay, we're like, hey, we just did that. Motional EMF. What's up? Check. No big deal. Okay. The second experiment, very same setup, same type of magnet. Actually, let's move this over a little bit. We'll see why in a second. Same loop of wire, probably a resistor, I'm guessing, although I don't know for certain. But in this case, Faraday pulled the magnet to the left with a speed v, and again discovered that a current I flowed through the loop. That might be a little small for y'all, I apologize. And finally, experiment number 3. So we'll get to this one because we're like, that's slightly different, but your intuition might be like, that should be the same. That's good intuition. Intuition in electricity is not always helpful, but in this case that is. So in the third one, same magnet, same loop of wire, and in this instance, both the magnet and the loop were at rest. They were not moving, and Faraday changed the magnetic field. So what we could say is the change of the magnetic field over time was non-zero, and he did this with an electromagnet. He discovered that a current also flowed through the loop. So let's put some math to this. What's going on? The first experiment, we're like I said, we already did this. We know. The EMF, the electromotive force, the force per unit charge is equal to the negative rate of change of the magnetic flux. In the second one, so you're like, but okay, if you were sitting on the magnet, the loop of wire would look like it's moving, just kind of like how you're in a car and you know you're moving because you see things passing you, but to you it looks like the trees are moving and you feel like you're at rest. So if you were hanging out, sitting on the magnet and watching the loop of wire, it would look like the loop of wire was moving. So, but wait a second. Remember from the last video, and if you know stuff about magnetic fields don't do work. So what's happening here? This is Faraday's discovery. So Faraday discovered that a changing magnetic field induces an electric field. And then it's the electric field that causes the EMF and the current to flow. And so in this case, we have an EMF that's equal to the path integral E dot dl around the loop of wire. And Faraday discovered this experimentally. He found that it is equal to the negative rate of change of the magnetic flux. Okay, that's fair. You're like, okay, like that's a pretty rad discovery, but what about this third experiment? This is totally different. Nothing is in motion. We're not talking about relative motion here. It's a changing magnetic field. So what the heck? Yeah, that's a fair point. And Faraday discovered experimentally that you get the same thing. Holy moly, this is wild. Okay, so let's take a step back and ask, how is the electric field related to the magnetic field? So Faraday discovered that this path integral, E dot dl, equals the negative integral of the magnetic field. I believe that is a vector. Yeah, it has to be a vector because it's dot dA. I like to go to the, this is the integral form. I like the differential form because it's easier for me to read. It's easier for my brain to read. So you apply Stokes's theorem and you get the curl of the electric field is equal to the negative rate of change of the magnetic field. And so from electrostatics, you might remember that the curl of the electric field is always zero. There's no spinny part to the electric field. It diverges, or it spreads radially outward like this. Whoops, wait, hold on. Arrows other way. So yeah, there's no curl. Curl is like this, where you have something that's like going around or whatever. But it turns out, well, if you don't have a magnetic field, aka if the magnetic field is constant, then this is zero, right? Because if you take the derivative of a constant, it's just zero. It doesn't change. A constant, by definition, is constant. It does not change over time. And so in that case, if B equals constant, then dB dt equals zero, and then this whole equation is zero, and you're like, cool, all of the electrostatic stuff holds, no problem. And what's really fascinating is that there are different forces at work here. So, okay, I do want to clarify. So this is actually the Lorentz force. And 2 and 3 are really Faraday's law. So we're gonna use some colors. So Lorentz force is number 1. And Faraday's law is number 2 and 3. And really, these equations are Faraday's law. Woo! Okay, so in the first one, remember, we moved the loop of the wire. It turns out that whatever is moving the loop of the wire is the thing that's doing work, whether that's me or if I attach it to my dog pulls the loop of wire and is like, what am I doing? Why? It's an experiment. You're part of history, Marley. Or however it ends up moving, there is work that has to be done on this loop to move it, and that is what is, well, doing the work. It's not the magnetic field. Magnetic fields cannot do work. So, but that said, like, it's the magnetic force is in play in experiment number 1. In experiment number 2 and number 3, the changing magnetic field induces the electric field, and it's the electric field that is doing work. That's pretty wild. We have 2 different forces, but we end up with this universal flux rule, which basically says, let me make sure that I get the wording right. Whenever the magnetic flux through a loop changes, an EMF equal to the negative rate of change of the flux will appear in the loop of wire. So this is wild and weird and cool, and Einstein thought so too. So these experiments, Faraday's law, was really the foundation for Einstein to be like, what the heck is going on? How can you have 2 separate forces giving the exact same result? How could we get a universal flux law if there's 2 different forces that are at work? And this is his motivation, this was Einstein's motivation for his special theory of relativity. QED, as they say. So I love that, right? And this is why it is so wonderful that we are able to build on top of the knowledge of folks that come before us. You know, there are always mysteries that we are left with and that we leave to future generations, and it lets us probe the universe and better understand our place in it. So I love this. It's so cool. And it's also a really helpful theory in the world. We use Faraday's law for all sorts of things, including motors and generators, speakers and solenoids, lots of other things. So yeah, I hope that you are as stoked about this as I am. Thank you very much for watching. Please let me know if you have any questions, and we'll see you next time. Bye, friends!